Hello all, my name is Abdillah and this is my colleague Alex. It is a pleasure to welcome you to today's webinar on managing data in ML AI projects. As we delve into the exciting world of machine learning, we are well aware that data is the lifeblood of any successful projects. Managing data efficiently is paramount. So in the next 45 minutes, we will explore on how data can grow and become more complex throughout the project. We are going to provide overview of what should be considered as data in ML project, what should be of concerns when managing data, and finally, how can we communicate the trained model in transparent way.
The process of developing a machine learning model can be quite complex. Abdullah, would you please explain what it is and why is it considered complex?
Sure. Let us focus on this diagram.
This diagram shows typical evolvement of a machine learning problem from its definition and raw data to a machine learning model. We start from a set of raw data. By performing multiple stages in an iterative way, we eventually end with a final selected ML model. The processes involve data quality checking and data cleaning, problem framing, data preparation, model training, model evaluation, and selecting the best model.
Okay, but where's the complexity lies?
Well, let me give you examples.
Let us focus on data quality checking and cleaning. There are many ways to check raw data. For example, you may want to check for its completeness, which basically checking if there is any missing data. Or you may want to check for its uniqueness, which basically checking if there is any duplicated data. Or you may want to check for its timeliness, which basically checking if there is any time slip on its timestamp. This is especially true if your data is time series or if you have time-bound requirement on one data relative to the other. And there are many other dimensions to consider when checking the quality of raw data, which includes readability, consistency, data type check, data format check, and etc. Once you understand your data and the quality of it, you need to decide to do something about it. You need to perform some data cleaning to improve the quality. If you have missing data, you have option to delete any incomplete records. Alternatively, you can perform imputation, which involves filling in missing values with estimated or calculated values. If you have duplicated data, you might want simply to delete any exact duplicated records. Instead of removing duplicates, you can flag by adding a new column that indicates whether a row is a duplicate. This way, you retain the information while allowing you to analyze the impact of duplicates on your results. If your dataset contains duplicates that need to be aggregated, you can use aggregation functions like sum, average, or maximum to combine the duplicate entries into a single record. In short, once you identify quality issues in your data, you can decide on various ways of performing data cleaning. In turn, this produces several versions of processed data. Hypothetically, you started from a set of raw data. Let's say you decided to have different ways of checking the quality. Based on the result of each data quality checking, you can decide on several ways of cleaning the data. Each cleaning procedure produces a version of processed data. Eventually, a set of raw data, once quality checked and cleaned, may result in several versions of processed data. Of course, in reality, due to time constraint and other limitations, you might deliberately select only one way of checking and one procedure of cleaning. Nevertheless, this illustration shows you on how a set of raw data, due to the decision when performing data quality checking and cleaning, may grow into several versions of processed data. Due to the need of reproducibility or repeatability, you need to keep track of data lineage. It is easy to lose track on what have been done to the data, what kind of processing, what kind of data transformation performed on the data.
Wow, okay. So the example that you elaborated just now underlined that in machine learning project, a single problem and a set of raw data in the beginning may evolve and grow into several versions of process data.
Yes, that's correct.
So far, we only demonstrated data quality checking and data cleaning, which already getting a little bit complicated. Remember that we have this full swing of processes. Similar complexity is also observed when performing problem framing. This is a systematic effort to understand, define, structure, and decompose the problem, which allows the formulation of hypotheses and/or approaches to solve the problem. A set of data and a single problem may be framed in different ways, which again leads to several hypotheses to attack the problem. Now, consider data preparation when you have several sets of process data and several problem framings. Each pair produces a set of featured data. In short, data management problem grows. As the project progresses, more data produced, more data transformed, more lineages to track to assure the reproducibility and repeatability. This is just a glimpse of complexity when developing machine learning model.
Okay, great. Now I think we can see and understand the complexity of handling all of those data involved in machine learning project.
Very good.
Previously, you mentioned about raw data and process data, and you indicated that it was just a glimpse. Could you give us an overview on all data involved in a machine learning project?
Yes, absolutely. First, let us go back to our favorite diagram, shall we?
Again, this diagram presents how typical machine learning problem evolves during a development project in order to produce the final model. How do we suppose to read this diagram? Well, this diagram uses crow's-foot notation. It is called crow's-foot because the symbols used to represent relationships often resemble crow's footprints. The arrow suggests the workflow direction. For each process, that is the purple box, there may be a need to return to previous processes in the workflow. Errors to indicate this have been omitted for the sake of clarity. According to traditional data science terminology, the term data in machine learning project generally includes raw data, process data, featured data, as well as training, validation, and test datasets. As such, the trained model, the model evaluation result, the final model, and also the detail of the problem framing are not usually included. However, from a data management and quality control perspective, they are considered data, which should be managed properly.
So you said in the perspective of data management, all of those boxes in white are considered data.
Yes, that's correct.
We need to pay attention to deal with them properly. We have raw data, process data, feature data, detail of problem framing, trained ML model, and evaluation score.
Let us start from raw data. Raw data is defined as unprocessed data. The term unprocessed indicates that processes are not yet done by the development team. However, it is possible that the data has been pre-processed, for example, pseudonymized by data provider prior to sending it to the development team. Upon collection, raw data may not meet the predetermined data quality requirements for its intended use, and therefore cleaning and pre-processing is often required. Organizing the data is usually necessary to standardize the format and structure of the data if it originates from non-standardized sources with varying format and schema. The result is a set of process data that is stored in an organized way to allow easy access during later processes.
Okay, so here we simply need to focus on the right-hand side. We have raw data and process data that have to be managed properly.
Yes, that's correct.
What's next?
Next is problem framing. It is a systematic effort to understand, define, structure, and decompose the problem which allows the formulation of hypotheses and/or approaches to solve the problem. This process produces details of problem framing.
I can see that in order to do problem framing properly, you need to not only understand the problem, but also the data.
Yes, understanding the data can be done by, for example, exploratory data analysis. But now, about details of problem framing.
Details of problem framing contains information such as learning type, learning task, required feature, target output, and model structure. Learning types refers to the way of machine learning algorithm learns patterns and makes prediction based on data. There are several fundamental learning types in machine learning: supervised learning, unsupervised learning, and reinforcement learning. Supervised learning is a type of machine learning technique in which the algorithm is trained on a labeled dataset. Unsupervised learning is a type of machine learning where a model is trained on a dataset without any labeled data. The objective is to discover hidden patterns and structures in the data, which can be used for clustering and similar applications. Reinforcement learning is a branch of machine learning that deals with training agents to make decisions in an environment based on reward and punishments. The next item of problem framing is learning task, which refers to the specific type of problem or objective that machine learning model is designed to address. Choice of learning task depends on the nature of the data and the desired outcome. These include regression, classification, clustering, anomaly detection, recommendation, and etc. The next is features. Features refer to the individual input variables that are used to make predictions. Features are the key components of the data that the machine learning algorithm analyzes to learn patterns. Features can be thought of as the attributes or properties of the data points in your dataset. The next is target output. Target output is also referred to as target variable, dependent variable, or label. It is the primary focus of a supervised learning problem where the algorithm learns to make predictions or classifications based on input features in relation to the target variable. The last is model design or structure. It describes whether the machine learning solution consists of a single model or multiple models working together, or a composite model which works together with non-machine learning model.
I see. Details of problem framing should at least include learning types, learning tasks, feature variables, target output, and ML structure.
Yes, that's perfect.
We have discussed about raw data, process data, and details of problem framing. Now, let us talk a bit about feature data. Previously, we have mentioned about the definition of feature data. Process to do this is called feature engineering. But why do we need it in the first place? There are several reasons. Well-engineered features can significantly enhance the performance of a machine learning model. By providing the algorithm with more informative and relevant input data, the model is better equipped to identify patterns and make accurate predictions or classifications. Feature engineering can help reduce the dimensionality of the data, making it more manageable and efficient for the model. With fewer features, the model can train faster and be less prone to overfitting, where the model fitting noise in the data rather than the underlying patterns. Raw data often includes categorical variables, such as labels or text, which machine learning models cannot directly process. Feature engineering techniques like one-hot encoding or label encoding help transform these categorical variables into numerical features that can be used in the model. Feature engineering often involves selecting the most relevant features for a particular modeling task. This helps remove noise and reduces the risk of overfitting, making the model more interpretable and efficient. Feature engineering allows domain-specific knowledge to be incorporated into the model. Experts in a particular field can create features that are more meaningful and representative of the problem being solved. Feature engineering allows for the creation of new features that capture interactions or relationships between existing features. These interactions can be important for certain types of predictive modeling. Feature engineering can include techniques to address issues like data skewness and outliers, which can impact the performance and stability of machine learning models. And last but not least, feature engineering can lead to more interpretable models. By creating features that have clear and understandable relationships with the target variable, the model's predictions become more transparent and actionable. All in all, there are unlimited numbers of feature data that may be produced from a set of process data. Therefore, feature data must be managed, their origin, methods, and processes on how they were produced must be properly documented and managed.
So, you said that feature engineering is very important. However, in the context of deep learning, if I remember correctly, this aspect is typically learned by the model itself.
Indeed, deep learning models can automatically learn features from raw data, reducing the need for manual feature engineering. However, this does not render feature engineering entirely unnecessary in deep learning.
Okay, so far we have discussed about raw data, process data, detail of problem framing, and feature data. Let us proceed to discuss machine learning model. Machine learning model can be trained from a broad range of algorithm types and setup. Some of them can be categorized as parametric, non-parametric, and ensemble methods. Parametric algorithm is a learning algorithm that summarizes data with a set of parameters of fixed size, independent of the number of training examples. Parametric machine learning algorithms include linear regression, logistic regression, linear discriminant analysis, naive Bayes, and simple neural networks. On the other hand, non-parametric algorithm is algorithm which cannot be characterized by a bounded set of parameters. It means that it does not make strong assumptions about the form of the mapping function between the features and the target variable. Non-parametric algorithms include k-nearest neighbors, decision trees, and support vector machines. Next is ensemble methods. Ensemble methods combine multiple machine learning models to improve predictive performance. Examples include random forest and gradient boosting. Now, this illustrates the broad range of machine learning algorithms. The respective hyperparameters and parameters make it difficult to store the trained model in a relational database with a fixed schema. Therefore, they are best stored as a file, for example, pickle file, and only the metadata should be stored in a relational database if necessary.
Wait a minute. Before you continue, please help us to understand more about metadata.
Sure.
Metadata related to a machine learning model may include pre-processing techniques, model structure and submodels, if any, algorithm for each model and or submodel, hyperparameters, parameters, cross-validation technique, model performance metrics and scores, and output processing routine. Pre-processing technique refers to the processes of extracting features from input data, as well as any necessary scaling. These processes may be quite complex. Therefore, it might be better to provide a combination of short descriptions in free text format and a pointer to a particular function or code where the feature extraction is implemented. Machine learning model metadata should clearly describe model structure and submodels. Machine learning solution may consist of a single model, or multiple models working together, or a composite model which works together with non-ML model. There are many reasons why we need multiple model structure. For example, Submodels might be necessary if a problem must be solved in several consecutive stages. In addition, a single generic model may not be sufficient to recover the whole problem space. Sometimes it is necessary to segregate the problem into several subproblems and build machine learning models separately. For instance, a machine learning model to predict life expectancy may consist of several submodels. Each submodel represents a different health domain or risk factor. All together contribute to the life expectancy prediction. A composite model, which consists of machine learning model and non-ML model, may be needed. You can simplify the problem into subproblems, and then one of the subproblems may be best to solve using non-ML model. The reasons can be due to lack of data of that particular subproblem, or required by regulation, or availability of well-performed non-ML model. When it comes to algorithm for each model and submodel, machine learning model metadata should specify what algorithm used for each machine learning models. Next, hyperparameters and parameters. Hyperparameters refer to any configuration which controls the learning process. A hyperparameter is often set by the data scientist and is independent of the training data. Different machine learning algorithms have different sets of hyperparameters which need to be tuned accordingly. Examples of hyperparameters for SVM support vector machine algorithm are regularization parameter to reduce the error by avoiding overfitting, and kernel type to go to higher dimensions. You can use either linear kernel, polynomial kernel, RBF, radial basis function kernel, sigmoid kernel, or even pre-computed kernel using provided data matrices. Examples of hyperparameter for KNN classifier algorithm is the number of nearest neighbors, weight function used in prediction, algorithm used to compute the nearest neighbors, and the distance metric used for measuring similarity between data points. Examples of hyperparameter for decision tree algorithms are the type of function to measure the quality of a split, the maximum depth of the tree, and the minimum number of samples required to be at a leaf node. Hyperparameters must be decided prior to the training. There exist techniques to perform hyperparameter tuning to optimize the configuration of the hyperparameters. For examples, grid search and randomized search. Grid search is a systematic and exhaustive approach to hyperparameter tuning. While it ensures you explore all possible combinations, it can be computationally expensive, especially when dealing with a large number of hyperparameters or a wide range of values. Randomized search is beneficial when you have a large hyperparameter search space and you want to explore a diverse range of possibilities without testing every single combination. It can be computationally more efficient than grid search, as it typically requires fewer iterations. Now, parameters. A set of parameters of a particular machine learning algorithm determines how input data is transformed into the desired output. Parameters are estimated from the data. For linear and logistic regression models, for example, typical parameters are intercept and estimated coefficients. Intercept is usually an array of size equal to the number of targets. Estimated coefficients can be 1D array of length of number of features for a single target, or it can be 2D array for more than one target. What about non-parametric models? Well, we may call them models attributes. Model attributes describe everything about the non-parametric machine learning model. For instance, k-nearest neighbors. K-nearest neighbors is a bit special as it is often referred as lazy learner. Lazy learner means that the algorithm does not use the training data points to do any generalizations. Lack of generalization means that K and N keep the entire training dataset. During prediction, the model finds the K data points from the training set that are closest to the input data points based on a distance metric. For decision tree, it has many attributes such as tree structure, total number of nodes, maximal depth, depth of each node, feature used to split at each node, threshold value, number of training samples reaching the node, and impurity at each node. Another item in machine learning model metadata is cross-validation technique. Cross-validation is a crucial technique in machine learning for assessing the performance and generalization capabilities of a model. It helps estimate how well a model will perform on unseen data and provides a more robust evaluation of its effectiveness. Cross-validation involves splitting the available data into multiple subsets. The model is trained and validated multiple times, with each fold used as the validation set once, while the remaining folds from the training set. Here, the red fold is the validation fold, and the rest blue folds are the training fold. For each iteration, the model's performance is evaluated on the validation set, and the performance metric is recorded. After all iterations are completed, the performance metrics from each fold are typically averaged to provide an overall estimate of the model's performance. Model testing is an integral part of ML model development. The model is evaluated on the test dataset, which should not have been exposed in the model training. Data leakage, the accidental use of sharing data or information between the training and test datasets, must be avoided due to its tendency to overestimate the performance of the model. At minimum, the documented model evaluation result consists of evaluation metrics, performance score, description of the test dataset, and the description of the relevance or meaning of the performance score to the problem. Different machine learning tasks have different ways to measure model performance. For regression, typical metrics are mean absolute error, mean squared error, root mean squared error, R squared or coefficient of determination, and adjusted R squared. For classification, typical metrics usually have an association with the confusion metrics, accuracy, precision or positive predictive value, recall or sensitivity, specificity or true negative rate, F1 score, or other aggregative metrics such as AOC, which stands for area under the ROC curve. ROC curve itself, or receiver operating characteristic curve, is a graphical plot that illustrates the performance of a binary classifier model at varying threshold values. The ROC curve is the plot of the true positive rate against the false positive rate at each threshold setting. For clustering, typical metric is silhouette coefficient. A higher silhouette score indicates that the clusters are well separated and appropriate, while a lower score suggests that the clusters may overlap. The figures above show how the data is clustered into different numbers of clusters and the corresponding silhouette score. The output of a machine learning model produced by its inference process might not be readily readable by humans. For example, the output of classification task might be binary number, that is 0 or 1. A routine to convert the output of machine learning model to human readable format should be made available and specified here. To summarize, data in a machine learning project includes raw data, processed data, details of problem framing, which consists of description on learning type, learning task, required features, target output, and ML model structure. And then also feature data, machine learning model, and machine learning model metadata. Machine learning model metadata contains description of pre-processing techniques, model structure and submodels, algorithm for each model and submodel, hyperparameters and model parameters or attributes, cross-validation technique, model performance metrics and scores, and finally output processing routines.
Okay, now we have full overview of various data in ML AI development projects.
Yes.
Could you tell more about typical considerations when managing such data?
Sure.
Data collection. Data collection is the process of gathering relevant and representative data that the machine learning algorithm will learn from. This data forms the foundation for training and testing the model. The quality and quantity of the collected data significantly impact the performance of the machine learning model. Data collection is not necessarily part of the data science framework. This process applies especially when data was collected for a certain purpose, which then at later stage is repurposed for building AI ML models. Lately, data collection is increasingly proposed to provide data specifically for building AI ML models. Focus on the need. Prior to collecting any data, it is important to focus on the data that is actually needed to reach the objective of building the AI ML models. Define and document it. Data to be collected should be decided, defined, and documented. Deciding what data to collect includes decisions about what type of information is needed and how should the data be collected. No ambiguity. Each data element should be defined in a way that leaves no ambiguity for humans or computers, both during the collection and during the processing or modeling. For example, age. Ambiguity arises if the term age is not clearly defined. Does it refer to the age at the time of data collection, the age at the time of a specific event, or some other criterion? Without a clear definition, different people might interpret age in different ways, leading to inconsistent and unreliable data. Next, metadata. Metadata may be outlined as a way to define the data more precisely. Here, metadata is defined as information that describes the data element. As a minimum, it should include data type. Other details to include could be unit of measure, semantic and pragmatic validity range, unique identifier, short name, long name, information about whether it is a derived value or measured value, expected or preset precision, information about whether it is compressed on how it is compressed, as well as related parameters such as deadband, deviation range, etc. Data sources. Data may originate from databases, survey and questionnaires, web scraping, sensor data, logs and records, social media, text and documents, images and videos, audio data, simulation data, etc. Knowing various sources of data in machine learning project is essential for making informed decisions. For example, some data sources, such as social media or surveys, may involve privacy and ethical considerations. Being aware of the origin helps in implementing responsible data practices, including obtaining necessary permission and ensuring compliance with privacy regulations. Knowing potential data sources helps in assessing the feasibility and availability of data. Some sources may be easily accessible, while others may require more effort, resources, or permissions to obtain and use. The design of data collection should consider the possible necessity to control the quality of the collected data. Data quality may consist of semantic, pragmatic, and syntactic qualities. It is optimal to handle and fix those three data qualities at the data source. At later stages, this can be more difficult. Semantic quality refers to what degree do the data correspond to represented the actual phenomena. Pragmatic quality refers to what degree is the data suitable and worthwhile for a given use. And syntactic quality refers to what degree do the data conform to stored metadata. It is optimal to handle and fix those three data qualities at the data source. At later stages, this can be more difficult. Careful design of data collection may save a lot of time and resources during data preparation. Okay, in summary, data handling considerations during data collection at least include focus on the need to find and document it, no ambiguity on the data description, equip the data with metadata, be aware of various data sources and consequences, and data quality control at source. So, as you can see, there are many things to consider even before the arrival of the data. Once you acquire your data, the next is data understanding. Data understanding focuses on describing the data to assess its quality and suitability for the intended modeling. Common way to achieve this is by performing EDA, exploratory data analysis. It is an approach to analyze datasets to summarize their main characteristics, uncover patterns, relationships, anomalies, and key insights. At the end of this stage, it will be decided whether the data is sufficient for the modeling phase, whether and which action should be taken to obtain more or better quality data, or whether the project goals should be adjusted. Data engineering competencies is required to collect and prepare the data. Data science competence is required to develop an understanding of the properties and possibility shortcomings of the data. Key considerations related to data quality include checking for missing data, syntactic quality issues, pragmatic quality issues, and semantic quality issues. Though semantic quality issues might be difficult to assess at this stage, this concern should be handled during data collection. I think before continue, we need to pause a bit here. Previously, we touched upon data quality issues, and I provided you with examples of some of those issues. Now, here I mention about three main data quality dimensions: syntactic, pragmatic, and semantic qualities. Maybe you ask yourself, what are the dimensions? Is there any checklist somewhere? Well, no worries. I'm going to provide you with exactly those. Examples of checklists for syntactic data quality issues include inappropriate data type for variables, such as representing numerical data as text, variability in the formatting of dates, times, or other numerical values, making it challenging to maintain a consistent structure. Errors in text data due to misspellings or typographical mistakes that affect the correctness of the information. Uneven use or improper nesting of parentheses, brackets, or other delimiters. In this example, the details field in the second item of the data array contains a string, single detail, instead of an array. This inconsistency in data types within the details field may lead to errors during processing, especially if the processing logic assumes that details is always an array. Presence of missing or null values in fields where data is expected, leading to gaps in the dataset. And variation in the units used for measurements, such as mixing metric and imperial units, without proper conversion. Okay, I know that this can be a pretty long checklist, but the list can be longer in reality. So bear with me. Let us continue to pragmatic quality. Pragmatic quality refers to what degree is the data suitable and worthwhile for a given use case. Let's say the use case is assessing cognitive impairment. Example of checklist of pragmatic quality for this case include the use of different cognitive assessment scales or instruments across studies, insufficient data on demographic factors such as age, education, and socioeconomic status, variability in the granularity of data, such as differences in the frequency of assessments or follow-up intervals, and etc. Semantic quality refers to what degree do the data correspond to represented the actual phenomena. Related data which did not adapted or validated for specific populations may produce biased results. Therefore, cultural differences in, for example, language, norms, and educational backgrounds should be considered. Another example of issue related to semantic quality is the lack of sensitivity of assessment to subtle change in the cognitive function, especially in the early stages of impairment. This can result in underestimating the severity of cognitive decline. Okay, now what if the data we have suffers from any of those three qualities issues? What should we do? If data quality issue exists, is there any chance to fix it at the source and have it resent? Otherwise, we need to deal with it. Another important concern to consider during data understanding is to evaluate the representativeness of the data in relation to the use case or problem in hand. Representativeness refers to the extent to which a dataset accurately reflects the characteristic of the broader population or phenomenon it is meant to represent. In other words, a representative dataset is one that provides a faithful and balanced representation of the various patterns, trends, and variations present in the real-world data it aims to model. Key considerations for data representativeness include population coverage, feature distribution, temporal consistency, geographical and cultural representativeness, and bias mitigation. Population coverage means that the dataset should cover a diverse range of instances from the target population. It should include examples that capture the full spectrum of variability in the real-world scenario. Next is feature distribution. The distribution of features in the dataset should mirror the distribution in the actual population. This ensures that the model learns patterns that are relevant. If the data spans multiple time periods, it should maintain consistency with the temporal patterns and change present in the real-world scenario. This is crucial for tasks where trends evolve over time. If the target population exhibits regional or cultural variations, consideration of geography and cultural factors should be taken into account. The dataset should be representative of these aspects. And finally, bias mitigation. Efforts should be made to identify and mitigate biases present in the data. Unintended biases in the data can lead to biased models, especially when the data does not fairly represent all subgroups. Okay, in summary, these are 5 key considerations for data representativeness: population coverage, feature distribution, temporal consistency, geographical and cultural representativeness, and bias mitigation. Now, what if the data was found to be inadequate for the defined problem? What should we do? Well, there are 2 options. First option is to consider obtaining more and better quality data. And the second option is to consider adjusting the project goal. That was all for data understanding. The next stage is data preparation. Data preparation focuses on selecting the data, fixing data quality issues, constructing, integrating, reformatting, and harmonizing the dataset to make them ready for input to modeling. Feature extraction, encoding, and embedding occur as part of this step. Data harmonization refers to efforts to combine data from different sources and produce a comparable dataset. This process usually involves data mapping from the original format to a standardized format. Data handling considerations during data preparation stage include addressing the data quality issues and adapting the format of all relevant data fields to enable subsequent data analysis and modeling. Modeling includes iterative processes of data splitting, data transformation, select algorithm, decide hyperparameters, perform model training, model evaluation, and adjustment until satisfactory results are obtained. In each iteration, adjustments can be made to the training data partitioning, train validation, feature extraction, and training strategy, that is, cross-validation, hyperparameter tuning, etc. Data handling consideration in the modeling stage focuses on maintaining model metadata correctly. This includes specifying the pre-processing technique, model structure and submodels, algorithm underlying the model, the hyperparameters and parameters, coarse validation techniques, and performance scores. The evaluation stage of the model assesses whether goals, success criteria, and requirements are satisfied. Even if the success criteria are not satisfied, evaluating the final model with respect to the project's objectives may provide a useful insight that can be used in the future iteration and/or other projects. Data handling consideration in the evaluation stage include updating the model metadata to cover outputs processing and getting understanding on the model sensitivity to expected data quality problems. Models in high-risk systems, such as clinical investigations, should be tested with extended test sets based on context-specific objectives. Deployment and monitoring. Deployment of the model, including the pre-processing codes to prepare the input data to its production environment, and subsequent monitoring of the performance of the model is carried out during its operation. Data handling consideration in this stage include issuing deployment plan, as well as issuing monitoring and maintenance plans. Assumptions underlying the application's operation should be sufficiently documented. During operation, the validity of the assumption should be monitored. Any contingency, redundancy, or fallback mechanism used in operations to handle wrong predictions or other application failure modes are sufficiently documented. Data quality of input data is continuously or periodically monitored. The same thing with performance of the machine learning application.
Yes, so that was it about the overview of data in AI ML development project and how we're supposed to manage it. Now, once we have the final ML model, how do we disseminate or communicate our model in a transparent way?
Transparent. Yes. While we are talking about it, do you know that transparency is one of 7 principles of responsible AI?
Oh, really? Would you care to elaborate more on it?
Sure, why not? The European Union has embraced the concept of responsible AI and has outlined 7 principles to ensure that AI systems are developed and deployed in a manner that is beneficial to society. Principles include human agency and oversight, technical robustness and safety, privacy and data governance, transparency, diversity, non-discrimination and fairness, social and environmental well-being, and accountability. In this session, we'll focus on transparency. Transparency principle underscores the importance of explaining both the technical processes of AI systems and associated human decisions. It advocates for AI decisions that are comprehensible and traceable, tailored to the level of expertise of the stakeholders.
That was about principles of responsible AI.
Yes, that's correct.
That looks great. But back to my original question, how do we communicate our model in transparent way? Any practical suggestion?
Fortunately, yes. Model cards. Let me explain. The concept of model cards was initially introduced by Mitchell et al. In their 2019 research paper. In principle, the model cards are concise documents that provide key information about the machine learning model, including its purpose, audience, maintainers, architecture, training data, performance metrics, limitations, and risk mitigation opportunities. Despite the growing importance of AI systems, many people lack an understanding of how they operate, and models are often deployed without a clear insight into their functionality. Questions like, in what scenarios does the model yield the most reliable and successful results? Or, are there any areas where it may not be as effective, need to be answered. Creators can use their in-depth knowledge to increase the trustworthiness of their AI systems by addressing relevant questions for a wider audience. Well-designed model cards can convey crucial information in a structured and accessible manner, engage both technical and non-technical experts, highlight innovations, and guide future models. Model cards can promote transparency, ethical AI, accountability, and awareness, help mitigate biases, and encourage consideration of impacts on various communities. They can help in finding, reproducing, sharing models, and reporting environmental impacts. A model card should be designed to be easily understandable, conveying key technical and non-technical details with consideration of the intended audience and their needs. For example, a model card for an AI system that helps interpreting X-rays is likely to be read by medical professionals, scientists, patients, policymakers, and developers. Various stakeholders can utilize model cards in different ways. MLOps engineers to assess and monitor model performance, AI model developers to compare results with other models, policymakers to understand ML systems implications, organizations to decide on ML technology adoption, impacted individuals to understand the model's operation or seek remedies.
Aha! Now we know. Why do we need model cards and who can benefit from them? But then, how do model cards look like?
Certainly. Let us elaborate on the proposed format. Model cards strive to standardize reporting on deployment-ready models by incorporating traditional, ethical, inclusive, and fair metrics, aiding stakeholders in decision-making and promoting forward-thinking model analysis. Model cards include sections on model details, intended use, factors, metrics, evaluation data, training data, quantitative analysis, ethical considerations, caveats and recommendations, each of which will be detailed in subsequent slides. Model detail section provides information about the model, including its developers, creation date, version, architecture type, associated resources, licensing, and contact information for feedback. Intended use section describes the primary purposes and target uses for which the model was developed, while also specifying scenarios or contexts where the model should not be applied. Factor section highlights factors like various groups, instrumentation, and environmental conditions that may affect model's performance, and how these were addressed for a comprehensive evaluation. Metric section describes model's performance evaluation measures, eventual thresholds applied to its outputs, and how they handle variability and uncertainty along with rationale for their selection. Evaluation data section provides details about the datasets used for model performance assessment, including their sources, selection rationale, pre-processing steps, and any special considerations. Training data section provides information about the dataset used to train the model, including its source, size, distribution, pre-processing steps, and any inherent limitations or biases. Quantitative analysis section provides an in-depth performance analysis of the model across various factors and groups, presenting both individual, unitary, and combined, intersectional results for subgroups. Ethical consideration sections addresses the implications of using the model, including issues like data sensitivity, human life impact, mitigation strategies, potential risks, and controversial use cases. Caveats and recommendations section highlights previously unaddressed concerns or limitations, suggests further testing, points out underrepresented groups, and suggests best practices or ideal dataset characteristics for model usage.
Okay, that was it about model card. Now, to wrap up our webinar today, first, we all understand that a machine learning project is complex. And managing data in AI ML project is challenging. Even more so when we realize that all inside the red boxes are in fact data. In a machine learning development project, data management problem grows. As the project progresses, more data produced, more data transformed, more lineages to track to assure the reproducibility and repeatability. All these should be managed properly. Data in a machine learning project includes raw data, processed data, details of problem framing, which consists of description on learning type, learning task, required features, target output, and machine learning model structure. And then also features data, machine learning model, and ML model metadata. Machine learning model metadata itself contains description of pre-processing techniques, model structure and submodels, algorithm for each model and submodel, hyperparameters and model parameters or attributes, cross-validation technique, model performance metrics and scores, and finally, output processing routines. And finally, once we have the trained model, we want to communicate the model in a transparent way. Model card is an alternative for it.
As we draw to a close, I would like to express our gratitude for your participation in today's webinar. Thank you for being a part of this knowledge sharing experience. We look forward to seeing your machine learning project flourish. Until we meet again, take care and have a wonderful day.